In this slide, we have an example of the future value of an ordinary annuity. So let's calculate the value of an ordinary annuity of $1,000 that earns 7% at the end of the 5 years. The chart below graphically shows the cash flows. As you see in here, first cash flow occurs at the end of the first year, second cash flow at the end of the second year, third cash flow at the end of the third year, and the fourth one is at the end of the fourth year, and finally fifth cash flow occurs at the fifth year. The first inflowing cash flow compounded 4 times, 1, 2, 3, and 4 times. Therefore, the value of $1,000 that comes in at the end of the 1 year grows into $1,311 after 4 times compounding. So this is the simple future value of a single sum formula, which gives us the value of $1,000 that is received at the end of the 1 year as of end of year 5. Similarly, second cash flow compounds 3 times and compounds to 1,225 years, and so on. And when we aggregate all of these, we get a total of $5,751 as future value of $1,000 annuity. One quick note in here, as you see in here, the fifth cash flow that comes in does not compound at all, and we take the value of that cash flow as it is, and the total aggregated value turns out to $5,751. So in a 5-year ordinary annuity, the first cash flow compounds n minus 1 times, second cash flow compounds n minus 2 times, third cash flow compounds n minus 3 times, and so on. In this slide, we are going to derive a general model or formula for future value of annuity. Although calculators in Excel does the calculation for us, it is good to understand the underlying arguments in the formulas that are used in calculation of the future value of annuities. So here we pretty much replicate what we have done in the chart in the previous example. So in order to calculate future value of an annuity that is equal to A for each period over an n-year period, when we earn interest I. So the first cash flow comes in and is compounded by n minus 1 times. Second cash flow comes in and is compounded n minus 2 times. Third one compounds by n minus 3 times, and so on. And the last cash flow, as we mentioned, does not compound at all. So this is almost replication of the previous example by using symbols. A representing annuity cash flow, I representing interest rate, and representing the number of years where the cash flows are going to be received. Now, if we do a simple manipulation in here, multiply both sides of this equation with 1 plus I, we get this equation where the left-hand side turns out to be future value of annuity times 1 plus I. On the right-hand side, since we are multiplying this with 1 plus I, the power increases by 1. So this term becomes A times 1 plus I to the power n. Second term becomes A times 1 plus I to the n minus 1, and so on. And the last term in here is multiplied by 1 plus I again. So let's call this equation 2. Obviously, since interest rates are positive, equation 2 produces a larger value than equation 1. And if we subtract equation 1 from equation 2, a lot of terms in the equations cancel each other out, and only two terms survive. So 1 plus I to the power n and this term that we have a are the two surviving terms. Since we are subtracting 1 from 2, that has a minus sign in front of it. And if we rearrange this equation, we take future value of annuity out of a parenthesis. So inside we have 1 plus I minus 1. And on the right hand side we have, we create the parenthesis and take a out, and 1 plus I to the power n minus 1 is the remainder of the term in here. And on the left hand side, ones cancel out, so we have future value of annuity times I equal to a times 1 plus I to the power n minus 1. And if we solve this for future value of annuity, we get a times 1 plus I to the power n minus 1 divided by I. So this is the general formula for future value of annuity. Provided that we have annual cash flows of A, we earn interest of I%, and we receive these cash flows over an n-year period, future value can be calculated by using this formula. Indeed, Excel and calculators utilize this formula to calculate the future value of an annuity. In this slide, we have an example of calculation of the future value of an ordinary annuity using a financial calculator and the Excel sheet. So in a financial calculator, we input the recurring payments that are annuities. For instance, in our example, the recurring annuity was, or the cash flow was $1,000. Then we enter the payment button in the calculator. The next argument is the number of years, so enter 5 for n. And then the third argument is the interest rate, which is 7%. Instead of percent or decimals, most calculators take the interest rate as integers and press I to input the interest rate. And then the next thing that we have to do is to press on future value button that produces the future value of annuity by utilizing the formula that we just reviewed. In Excel, we are going to use the future value function, but this time we are going to input recurring payments as an argument. So we use future value, and then the first argument, as in the future value formula, is the interest rate, which is on B3. The next argument is B4, which is the number of years. The third argument is the payment or recurring cash flows, which is in B2. We input this with a minus sign in order to get a positive future value of an annuity. There are two additional arguments here that are left blank. You don't have to fill those. The second argument is the present value. If you start the period with a certain amount of money, we could enter that present value, that is the amount that exists at time 0. But in this case, we don't have anything. Therefore, we will either input 0 or leave blank. And the third argument is the type of the annuity. For ordinary annuity, the argument takes the value of 0. But if we skip it, by default, Excel assumes that this stream of annuities are end of period cash flows, and it is going to treat it as an ordinary annuity. And once we enter, future value is produced in this cell 5, B5. So essentially in cell B5, you're going to write this formula, and it is going to produce $5,750. If we implement the formula that we used, A is the annuity, in this case $1,000. 7% is the interest rate. We will enter in the formula in decimal form 0.07. N is 5 years, so to the power 5 minus 1 divided by interest, which is 0.07 or 7%. That also produces 5,750 point, it should be 74. I think this is a typo. So one thing maybe to remember is to enter the payment as a negative value in order to get a positive future value in Excel. If you enter the 1000 as a positive figure, the formula is going to produce a negative number. This is how the function works in Excel. On the left hand corner there is a function sign, and if you click on the function sign you will get this window, and the arguments are in order in here. As we mentioned, the first argument is rate, which is the interest rate. The second argument is number of periods. Third argument is payment. The fourth argument is the present value. Fifth argument is the type. So in our formula we would fill only rate, which is 7%, number of periods 5, and payment minus 1,000, and that would produce the $5,740.74. So this is how the function works in Excel, and you could launch this by just simply clicking on the function button in Excel. In this slide, we derive the formula for annuity due. As we mentioned earlier, the first cash inflow comes at time 0 and is compounded n times. Second cash flow comes in at time 1 and compounds n minus 1 time. And the last cash flow comes at time n minus 1, or in this particular case at time 4, and it compounds 1 times. And this constitutes equation 1. If we divide both sides of the equation to 1 plus I, on the right hand side we get 1 plus I to the power n minus 1, and finally the last argument that we have, once it is divided by 1 plus I, turns out to be a. And if we subtract this time 2 from 1, if we subtract 2 from 1, because 2, as you see in here, is a smaller figure or number than the equation 1 is going to produce, so you will take the larger one and subtract the smaller one. And when we do this, we have future value of annuity minus future value of annuity divided by 1 plus I, which is the second formula. And when we do the subtraction, a lot of figures or terms are cancelled out. Only surviving ones are the first one in here, which is a times 1 plus I to the power n, and the last one in the second one, which is a. So as in the previous case, if we rearrange the equation, we simply get future value of annuity that is equal to 1 plus I times a times 1 plus I to the power n minus I divided by I. If you notice that this part in circle is exactly the future value of ordinary annuity, and the only additional term in is 1 plus I, which suggests that there is an additional period of compounding when annuity is due. So that this shows that the future value of an annuity due is simply future value of an ordinary annuity times 1 plus I. That's why we said that annuity due is always larger than an ordinary annuity, or future value of an ordinary annuity. Uh, if we assume that the previous example that we had was an annuity due, that is the first cash flow came in at time 0, second one at time 1, and so on. As you see in here, the last cash flow occurred at time 4, and if we just simply compound each of these cash flows and sum them up, we get $6,153.29. And if we simply use the formula, we get 1 plus I times A times 1 plus I to the power n minus 1 divided by I, and simply that is $6,153.29. Or we could use the previous figure that we calculated, 5,740.74 times 1 plus 0.07, we will get the same number. In Excel, to calculate the future value of an annuity, we use the future value function, same arguments, that is the interest rate, which is 7%, inputted as decimals. And second one is the number of years. Third one is the cash flow. I did not put a minus sign in here, but it would be useful to put a minus sign in here to get a positive future value in annuity. So it should be a minus sign in here. And the next term, which is the present value, we input 0 there. And the last term, which defines the type of annuity. In this case, it is an annuity due, so we use logical argument 1 to indicate that the annuity is the type of annuity that is due, that the cash flow comes at the beginning of the period. So this produces 6,153.29 as in the other methods that we had. So now we are going to calculate we are now we are going, in this slide we will demonstrate calculation of present value of an ordinary annuity. We will do this through an example. In this example, Braden Company, a small producer of plastic toys, wants to determine the most it should pay to purchase a particular annuity. And this annuity consists of annual cash flow of $700 at the end of each year over a 5-year period. The required rate of return that Braden Company demands is 8%. We could also interpret this as the each cash inflow that comes in should have an opportunity cost of 8%. So in this example, in order to calculate the present value of the stream of cash flows, we are going to discount each cash flow that is going to be received sometime in the future 2 times 0. Since the opportunity cost is $700, meaning that if the company had an X amount of money today, it could invest that X amount to earn an 8% return. So the minimum amount that the company would accept for a $700 that is going to be received 1 year from now would be $648.27. So if the company had this amount, it could earn 8% interest and would go up to $700. Because if the company received any amount less than this, the future value would not be equal to $700. So we will discount to $700 one period, which is equal to $648.20. The second cash flow will be discounted 2 periods, so it is going to be divided by 1 plus 8% or 0.08 to the power 2, so discounting it 2 times or 2 periods produces $599.90. The third cash flow is going to be discounted by 3 periods to receive 555.80, and then the fourth cash flow is going to be equal to $514.50, and the fifth one is going to be discounted by 5 periods. As you see in here, the last cash flow that is received on year N will have to be discounted by N periods. And the total of all of these discounted values is $2,795.10. So this means that the most that the company should pay for this stream of cash flows should be $2,795.10, because if the company pays any amount larger than this, the amounts that are going to be received is going to be less than what is being paid. So if, for instance, the company paid $3,000 for this stream of cash flows, it would be buying $2,795.10 at a value of $3,000. Obviously, that would not be rational. So the present value of this stream of cash flows is then equal to $2,795.10 as of time 0. We can derive the present value of ordinary annuity in a similar fashion as we did in the future value of annuity. If you remember, the first cash flow is discounted by 1 period, the second cash flow is discounted by 2 periods, and third one 3 periods, and so on. And so the nth cash flow is discounted by n periods. So this is our first equation. We multiply this equation with 1 plus I to get this equation 2. When we do that, the first term in the equation turns into A, because we are multiplying this with 1 plus I. The second term turns into A times 1 plus I, because on the denominator there's another 1 plus I, so one of the 1 plus I's in here cancel out. And finally, the last term is going to be a to the 1 plus I to the power n minus 1. So this figure should be larger than the first equation that we have in here, or this equation is going to be larger than equation 1. So if we subtract equation 1 from equation 2, we get this equation. As a result of cancellations in here, there are only 2 surviving terms. The first term that survives is this first term in the second equation, A. And in the second equation, only surviving term is A divided by 1 plus I to the power n. And again, by reorganizing the equation, produces A times 1 plus I to the power n minus 1 divided by I times 1 plus I to the power n. So this is equivalent to what you see in here. So A times 1 plus I to the power n minus 1 divided by I times 1 plus I to the power n. If you pay a little bit attention to this equation, this is simply the future value of annuity discounted by n periods. So you can think of the present value as the future value of annuities discounted by n periods to time 0. An alternative representation is this one. If we cancel out this first term and the denominator in here, only I survives in here, and this turns into 1. In contrast, this term turns into 1 over 1 plus I to the power n. So both would work. You should remember one of these as a backup in case your financial calculator does not work or you do not have access to Excel. So if we look at the previous example, we could produce the solution by inputting payments as $700 over 5 years, n is 5. Interest rate or the opportunity cost is 8%, and simply use the present value button to get $2,794.90. In Excel, we use the present value function where the rate is the first argument, number of years is the second argument, the third argument is the payment. Again, we enter this as a minus sign to get $2,794.90. If we enter this as just B2, we will get minus $2,794.90. So we should be conscious of that, and either we can put a minus sign outside of the function in here, or we could input 700 as minus. And here you see the same thing by using the formula. So 1 plus I to the power n minus 1 divided by I, which is 8%, times 1 plus 0.08 to the power n, which is equal to 5. And this is the alternative representation in here, so the same things. In both cases, we get $2,794.90. And the present value function in Excel is something like that. Again, if you click on the function symbol on the corner of your screen on your Excel sheet, you will see these arguments in present value, and you can enter them in order. As long as the type of the annuity is ordinary, you don't need to fill up these last two items. But if the annuity is due, then we need to change the type to 1 because default is 0. So this is the alternative calculation where we use the annuity due. Now, in order to calculate the annuity due in a financial calculator, we need to switch the cash flow sequence to beginning of the period mode. Each calculator has a different way of doing this. I would suggest you to check the user's manual how to make that switch. It might be quite easy. Simply a button would help you to switch from end of the period to beginning of the period cash flow. So in this case, once we switch the cash flow mode to begin, we pretty much enter the same arguments. Payment as 700, number of years 5, interest rate 8%, and when we press the present value, we get $3,800.49. As in the previous case, an ordinary an annuity that is due, or an annuity due, is larger than ordinary annuity, and as the result shows in here, it is confirmed. When we use Excel, we use the same set of arguments. B3 is the rate, B4 is the number of years, minus B2 is the payment. Present value is entered as 0, and type of annuity in this case is due, therefore we change the last argument to 1 from 0, and that produces $3,018.49. And the same result can be replicated by utilizing the formula. So if we input the annuity, interest rate, and the number of years into this formula, we get $3,018.49. As you see in here, the annuity due, or present value of annuity due, is simply 1 plus I times larger than the present value of an ordinary annuity.